done. And then how's the other direction go? I vaguely recall moving the other direction, but I wouldn't have to do it again. Suppose you do have the condition in place. So we fix epsilon greater than 0, and there exists an n of epsilon such that whenever jointly n and m are greater than n of epsilon, that implies f n of x minus f m of x is less than epsilon for all x in E. Now we'd like to erase the m, so Cindy will tell I just erase that one. Okay. Okay. Well, remember what we did. The limit as m goes to infinity, pointwise limit of f m of x is f, right? So why don't we just apply that limit operation to the absolute value? It doesn't affect the first term, right? And it produces the unsubscripted f in the second term. This thing is always less than epsilon. How big can this be? It could be equal to epsilon, but not greater than epsilon. These things are always stuck strictly less than epsilon. The biggest this could be is the soup of all these, right? And let's let epsilon there is certainly less than 2 epsilon, which we define to be epsilon prime. And then we go back and say, fix epsilon prime. That's another little gimmick. So this is the epsilon prime that we're using. And then all the way through here, this is true. Anyway, right? So those are both directions of the Cauchy criteria for uniform convergence. And now we want to use that to establish Weierstrass's test. Which says, given a sequence of functions fn, defined on some common domain, if there exists an mn such that the absolute value of fn is less than fn for all x in E, and the sum of the mn's converges, then what? Phil read this on Tuesday. The sum, right, of the fn's converges uniformly. Okay, that's the Weierstrass M test. We can make it stronger. That's true as well. The Weierstrass test gives you two things. One, you don't even ask for it. It says it converges uniformly, and it also converges absolutely. There's some other little tests we ought to probably look at someday. The alternating uniform convergence test, Dirichlet's uniform convergence test. That'd be good stuff to put on the file. These are all things you can look up. I'm not sure you're going to find a proof on Google, but at least you can see it. Who knows? I guess you can find it on Google these days. If you can't find it on Google, you can probably find it, well, in, what's that new one?
Yes.
Wolfram Alpha. You seen that? No. Wolfram Alpha. Wolfram Alpha is a new thing. It's the Mathematica search engine, or the Mathematica calculating engine, coupled with the search engine. I'll tune it in here. We'll take a break in a second. I'll show you how. Anyway, okay. So we got this. So this is a one-way proof, isn't it? How do we prove this? Well, what do we have to show? Must show. Well, what did do it for us? Define the sum up to capital N is this sum. So Sm is this sum. And we can take n greater than m, which means if thunder, holy smokes, if we fix epsilon greater than 0, must find an n of epsilon such that whenever capital N and capital N are greater than capital N of epsilon, that implies that since n is greater than m, it's going to be bigger, right? So Sn minus Sm less than epsilon. Will that do it for us? All right. How can we arrange this to happen? We have a big resource here. We haven't even used these.
Shouldn't your sums Sn go from this 1 to capital W?
What did I do? Oh, geez, good. Absolutely. You know, oh God, this is an M. I specifically, yeah, you're absolutely right. I specifically said that. I think I might have even said it, and I didn't write it.
Yeah.
We're just going out to N, and we're just going out to M.
Obviously, your summation for S and M is absolutely like absolute.
Oh yeah, I'm really laying them out here.
It's the ends. Exactly.
I think here. This is what they are. S of n is the sum from little n equals 1 to capital N, absolute f n of x, Sm equals the sum from little n equals 1 to the same thing, f n of x. Okay, and you're assuming that capital N is greater than capital N, so that Sn minus Sm is going to be the sum from n equals m plus 1 to n, right? Of this. N is on beyond m. So the difference of these two, this takes away the first m term. So they're gone. So the first surviving term has index m plus 1, and we run out to n. So that's what this is now. How can we ensure, remember, we want this to be less than the given epsilon. How can we make that true? What do we have going for us? So go back and check that out. We have the majorizing numbers that converge as a series. So you suppose that this thing would certainly be less than or equal to the sum from n equals m plus 1 to n of the mn's. Just one for one. Each one of these is no smaller than its companion over here, right? And we're summing over the same indices, so this is certainly true. But what's this? This thing is the sum, what shall we call it? Sigma sub capital N minus sigma sub capital N. where sigma sum n is the sum from n equals 1 to capital N of the mn's. Scale. Right? So those are the definitions of sigma.